This is All Things Cancer, the podcast of the National Foundation for Cancer Research. Hosted by NFCR President and CEO Dr. Sujan Ba, each episode explores the hindsight, insights, and foresight of cancer research and care, and how NFCR and its partners are accelerating the path to cures. In this episode, we sit down with one of the most influential figures in cancer research, Dr. Tony Hunter, whose landmark 1979 discovery paved the way for over 80 targeted cancer therapies used in clinics today. Join us as he reflects on a life of science, discovery, and what the future holds for cancer research.
Hello, Dr. Hunter. It's so good to meet you today. I have heard your name for a long time. You are one of those iconic leaders I have always wanted to meet.
That's very kind of you.
You are celebrated as a recipient of the 2025 St. Gyorgi Prize for Progress in Cancer Research. I'd love to hear your view about this prize. And what does that mean to you?
Well, it's a great honor to have been chosen as the 2025 winner of the St. Gyorgi Prize and to join the distinguished list of other prize winners over the years, all people that I look up to and have made really fundamental contributions in cancer research.
Your discovery in 1979, the discovery of tyrosine phosphorylation that controls the cell growth division, really changed the fundamental understanding of cancer biology and medicine. And since then, there have been more than 50, maybe even 60 targeted drugs being applied now, used to treat patients. So this is amazing journey you have. Can you take us back to your early career stage, and you were educated in Cambridge, right?
Yes, I was educated at the University of Cambridge as an undergraduate and then continued then to do my PhD in the Department of Biochemistry, where I was studying mechanisms of protein synthesis. I didn't really have a burning desire to be a cancer researcher. We didn't have cancer in the family. But in 1971, I followed my first wife to San Diego, where she was going to do a postdoc at UCSD. And I ended up at the Salk Institute with Walter Eckhardt, who was studying polyomavirus, a small DNA tumor virus that was being used as a potential model for cancer. And so that's where I got my start in cancer research.
At the Salk Institute.
At the Salk Institute. And for 2 years, I started as a postdoc and became quite deeply interested in understanding how this virus caused cancer. But I went back to the UK for a year after my 2-year fellowship was up, started looking for a job, and no one wanted me in the UK, but luckily they'd offered me a position at the Salk Institute before I left as an assistant professor. And in the end, I came back in 1975 as an assistant professor and started working on polyomavirus again, this time more deeply trying to understand how the proteins the virus makes when it enters a cell cause the cell to become a cancer cell. And basically, I've been doing that for the last 50 years.
So you basically made the discovery early, very early in your career, only several years after you started your faculty position at the Salk. From Cambridge to California, that must be quite culture shock, right? From traditional conservative environment of Cambridge, UK, to a free spirit, very free spirit environment of California.
It was indeed a huge culture shock. Things were so different in California, particularly in La Jolla. But I soon adapted. I started to grow my hair, and then I grew my beard. I became very much a California hippie after just a few years.
And that really grew on you. The California hippie spirit really grew on you.
Yes, there were two reasons. First was the science. The science at the time was very exciting. Tumor virology was a new discipline, and breakthroughs were being made one after the other. The other reason I came back was to raft rivers. So while I was a postdoc, I had been indoctrinated into whitewater river rafting.
Oh, wow. You're a surfer, a
Well,
rafter.
not a surfer. No, I failed in surfing, but river rafting is also whitewater. And we had a trip in 1972, the first summer we were there, where we rafted the length of the Grand Canyon on the Colorado River. And I really loved it. And it was the sort of wilderness you can't really find in Europe or in England particularly.
Indeed.
And so the other reason I came back was so I could do more wilderness activities. And for many years, about 30 years, we rafted a river somewhere in California or in Idaho every year.
And so that actually is a good combination of very bravery spirit. Explorer for science, explorer for wilderness, right? So that is your DNA.
I guess it is. I hadn't really thought about that, but yes, you're right.
And so when you discovered in 1979 the tyrosine phosphorylation phenomenon, I should call, and how well was that accepted by the mainstream of the research community?
In some ways, surprisingly, it was rapidly accepted. There were no naysayers. I think in the end, the data was so strong and many people could reproduce it very quickly in their own system. And so after we had reported this and talked about it in public, people just tested, in their own system and found it was true. And so there was really no doubt about it, which unlike some other discoveries where there's a lot of resistance in this case, no, it was widely accepted.
So you, in a way, you're very lucky, for the prepared mind, right? But lucky in so many ways. Your early discovery and quick adoption. That's a good combination to have.
When we found tyrosine phosphorylation, it was in the context of this polyoma virus that I had worked on as a postdoc, and then quickly another tumor virus called Rous sarcoma virus. But we didn't know at the time whether it would be important in human cancer. This was viral cancer.
Viral cancer.
But quite quickly it became clear, yes, that there are cellular enzymes that add phosphate to tyrosine, including growth factor receptors. And that told us, yes, the virus works by usurping cellular pathways to drive growth, proliferation. And so within a few years, we knew there were human oncogenes that were tyrosine kinases, and then the race was on to try and understand how they worked, and ultimately within a few years to develop drugs that target these aberrant tyrosine kinases.
And there are several examples. Gleevec is one of them.
Yes, Gleevec was really the poster child, and really I think people suddenly realized, yes, you could make these small molecule drugs. At the time, there was a fair amount of resistance to the idea that one could target enzymes like protein kinases that add phosphate to other proteins, because they use ATP, the energy source of the cell, and ATP is very abundant in cells. And people thought that drugs which had to compete with ATP for binding to the enzyme wouldn't work very well. But Gleevec showed them that wasn't the case. You could make small molecules that bound even tighter than ATP to these enzymes and therefore blocked their activity. And so once Gleevec was approved, everyone wanted to develop their own drugs. And as you said, it's actually over 80.
Oh, over 80 now
Over 80
already.
tyrosine kinase inhibitors, or TKIs, have now been approved for clinical use.
How do you feel about your impact?
Well, it's an incredibly gratifying outcome of doing experiments on a simple virus. There were people who doubted whether tumor viruses would tell us anything about human cancer, because in general, human cancer is not a viral. There is no viral etiology. But it turned out, yes, the viruses taught us a lot about cancer, not only tyrosine kinases, but many other critical pathways are targeted by viruses.
Yep. So since your discovery, and how much are you involved in translating this discovery? And then now, like you said, there are more than 80 targeted therapies targeting these tyrosine kinase inhibitors.
Yeah, fairly early on, we realized there was translational potential here, but we didn't have the skills to really take that forward. And at the time, there were no biotech companies. Now, if you've made a fundamental discovery, you can found a company to develop your ideas.
The first biotech company was in the mid-80s, right?
Right. So, this was in the early 80s, and there really wasn't any obvious way to translate. So we left that to other people, like Ciba-Geigy, in this case, developed the drug that became Gleevec. And I follow with interest. I have served on advisory boards for many small companies now that make these TKIs, but we never did it ourselves.
Alex Matter was one of the internal champion.
Yes,
for this,
absolutely. Ciba-Geigy, which became Novartis. Yes, and I know he won the prize a few years ago, right? So yeah.
So you pretty much provided the advisory role to all the companies developing the tyrosine kinase inhibitors.
Yeah, like Sugen, the company that Yossi Schlesinger and Axel.
That's another
Axel
one.
Ulrich founded, and several of their compounds are now in the clinic, and some others. It's been very exciting to watch. Of course, I don't have any chemistry skills, so I couldn't really help them with drug design, but I could help them with the biology. So,
and I think biology is the combination of innovative chemistry and critical biology exploration are the key to make drug molecules successful.
Absolutely agree. You have to understand how the drug works in the cell, and to make sure there aren't unwanted side effects. Surprisingly, some of the first approved TKIs, these kinase inhibitor drugs, are quite non-specific, but they still work.
They still work.
So,
but we are developing more and more targeted medicines, right?
Yeah, the technology has got a lot better now to be able to rapidly design small molecules through structure studies, and now particularly AI analysis, to get you a better design that's going to be more specific. And so the lead time between starting a project and getting a compound into the clinic is rapidly shrinking.
Yeah. But on the other hand, the cost of getting the discovery translated into the lead compound and get into the clinical pipeline skyrocketing. How do you feel about that? What's your view on that?
Well, it's at several levels, right? So the initial phase of designing a molecule and testing it in the lab is relatively cheap. I mean, it's millions of dollars, but the real cost comes in the clinical trials, as you know, which are incredibly expensive. Sadly, only 1 in 10 compounds that
will make it to the end.
You're right. It goes into trials is successful.
Yeah. But also, the preclinical stage, right? So when you have the discovery, you have a lead compound, and trying to identify the best lead compound, and then do all the testing to get to the IND. That is still the hardest space to get funding. Have you encountered any of the barriers, obstacles? What's your view on this?
Well, as you probably realize, particularly now, the success rate of grant applications to the NIH or to the National Cancer Institute is really low. It's around 10%. And so it's challenging to get grant funding to run the experiments you want to run.
Researchers we work with, they tell me it's easier to get grants for discoveries. And also it's easier to get the grants for clinical research to conduct a clinical trial, especially multi-center clinical trials. But it's very hard to find the money for preclinical testings. And that's where actually NSCR has expanded our efforts to help the scientists, help the entrepreneurs to translate their discoveries.
Right. I would say it's often called the Valley of Death, right? So
Yes,
you made the
exactly.
useful discovery, you've shown it in principle could be a viable target, but then getting to the next step, persuading, a bigger company to take it on and put it into clinical trials is very difficult.
And even the VC money, so they are less and less willing to invest in preclinical.
Right, because they know the
stage.
success rate is low.
Very low.
So they're keen to see a return on their investment sooner rather than later. And in the old days, as it were, VCs were willing to take the risk. They knew that not every company they invested in, small company they invested in, would be successful, but enough of them were that they could make a good return. But now people are more impatient. They sort of look on the technology side where you can see, return in just a very few years if in IT or computer technology, but it's not true in biology. Biology isn't so predictable as in the technology side.
And right now, like you mentioned, AI is really taking a hold in cancer research.
Right.
And what's your view about the AI's future role? How do you think we can actually make a good use of AI?
It's early days, I think, to
It's
know
early
how
days.
best to make use of it, but it's clear it's having an impact already in diagnostics. The real power right now is in analysis of huge data sets where it can meld different data streams and come up with a hypothesis as to how an interpretation of the data and maybe predictions or algorithms for predicting outcome, drug success, patient outcomes and things. So I think that's certainly the area right now. I know, for instance, Genentech has invested hugely in AI programs.
And Google Health.
And Google Health is also,
and the GE Health, all of them, right? But we haven't seen really good, successful example yet, right? And the AI, as much as they can aggregate all the large-scale data sets, but sometimes AI is still hallucinating.
It can still hallucinate, yes. So we have to, that is a problem that you have to face up to. You shouldn't necessarily believe what AI predicts. Have to validate it in another way.
So they still have to go back to the wet testing. So
I think ultimately anything that AI predicts, proposes, one has to test it.
So that's an added cost. Don't you think that's an added cost that contributes to the skyrocketing cost of discovery now?
I agree. Everything you do is expensive.
So it's harder and more expensive now. It really takes a brave spirit and persistence to go forward, to make a big impact.
Yes, you have to be willing to take a risk that what you're testing or what you're planning is not going to be successful. And as we know, in biology, probably 90% of the experiments you do don't work or don't tell you something meaningful, at least. And same is true when you start to do preclinical studies, that they won't all work.
So this, a low success rate must be quite challenging for the young generation of scientists to go into the, biomedical research. And how do you think we should do better to encourage the young people?
More funding, I think, is probably the bottom line. Luckily, there are, for people who just become a faculty member, there are scholarships and fellowships available that are not federally funded. So there are sort of startup awards. And so that
from
helps
the federal government.
No, these are not federal. These are private organizations.
Federal private organizations like NSR.
Right, exactly. So that enables people to get started and get the lab up and running, and then they can, if successful, apply for federal grants to keep the lab running. But still, again, the success rate is not very high, and There's a concern that, the next generation will be dissuaded from doing biomedical research because they see the challenges of getting a lab and being successful, and they'd rather have a more secure job, doing something
we
else.
heard that voice, right, from the strikes UC system, right? I think postdocs and teaching assistant had huge strike last year. Basically, they don't even get paid enough to have reasonable life.
Yeah, no, they didn't get a living wage, because California is so expensive,
yes.
right? And so there have, the postdocs and graduate students have both had large salary increases, which...
Oh, you have seen that?
Yes, which is...
From California?
Actually nationwide, actually.
The nationwide.
It's a big jump from around $55,000 a year to around $70,000 a year starting.
So at least that's decent for a living wage.
The issue is that our grants are not increasing in parallel, and so the large, it's well-deserved increase in salaries is eating into the budget, meaning that we have less resources available to do the research. And so there's a catch-22 there. You're not, yes, you pay your staff a living wage, but you can't afford to do the research.
And how are you overcome that in your lab? You have a big lab.
Not any longer. My lab is shrinking.
Because of the funding? Because
of the funding issues, right. And also NCI has cut its outstanding investigator reward system. And so that's making it difficult as well. The big challenge potentially is the cut in the indirect cost rate, because Salk has a very high indirect cost rate.
68%?
Ours is 90%. And
90%.
Has been ever since.
Wow, that must be the highest one among all the institutions.
Most standalone research institutions like Salk have about a 90% overhead rate, just because we don't have state funding or other sources of funding, and so that is really challenging.
Salk Institute is a nonprofit, right?
The Salk is a not-for-profit institution, yes, founded in 1960.
So if the government funding cuts the indirect costs, what kind of measures can institutions like Salk take in order to, make up the decrease in funding?
Well, economies, they'll make economies internally, let some people go, reduce some
so that's
services.
Sad. We are losing the research talents.
And then the other way they will cope is to whatever is being covered by the indirect costs will be charged to your direct costs. So they'll charge your grants for services that currently are free, as it were. So that will also reduce the amount of funding you have available.
It's really a domino effect.
It could be a serious domino effect, right?
So right now, America is still the leading force for biomedical discoveries. And do you see that kind of leading edge going to be reduced or compromised?
I think it'll be seriously affected, right? I mean, two levels. Funding is not going to be sufficient, and B, people don't want to come into this as a career. And we already know that China has overtaken the US in terms of its prominence in biomedical research. They've invested more money than the US has, and we're falling behind.
Talking about China is rising in biomedical, and in the past 20 years, U.S. and China were very collaborating about biomedical research, and lots of cross-border collaborations. But during the past several years, I have seen the dramatic reduction about this kind of collaboration. I'm pretty concerned because the biomedical research should not have a border, should not be affected by politics or geopolitical environment. What are your views about this?
No, I agree with this. Biomedical research should have no borders, but unfortunately, in the case of China, starting with the first Trump administration, there's been a bit of a witch hunt for Chinese-born scientists working in the US who have received funding from China one way or another. Maybe by having a second job in China, it's made it very difficult to have a collaboration with any Chinese research team. And I think a lot of people are not even trying now because we're not getting the influx of very talented Chinese scientists who would come in and either do a graduate studies or postdoc in the US and then stay and take academic jobs. And most of them not coming in now. They're not going to be, I think, get a visa to come in and be. Many of the Chinese-born scientists are returning to China to take up jobs in China. I just had one of my best postdocs tell me he's leaving WashU, where he's a tenured professor, to go back to Beijing, which is very sad.
It is very sad. I wonder whether this trend will continue. Do you see this trend has been accelerated in the past several years?
Yeah, I think it has been accelerating, and it seems to me it's unlikely to turn around anytime soon.
And you were the director of Cancer Center in the past at the Salk Institute. Tell me about your perspective as an institutional leader, and if you were the director of Cancer Center right now, what would you do to deal with all the challenges, barriers you see and we discuss here?
Yes, the Salk Institute has a National Cancer Institute, or NCI, Cancer Center Support Grant, a CCSG, which provides funding to support programs, particularly core services and some administrative work, and also some startup funds for new investigators. It's very important to the Institute. It comes fully overheaded, which is equally important. But we have one of the basic cancer centers, so that we don't have any clinical activities. And only 7 out of the 60 NCI designated cancer centers in the US are these basic cancer centers. So we can focus on cancer research. And that funding has just been, we've had it since 1973. It's been invaluable to the Institute in funding cancer research. My job as Cancer Center was to make sure that we were integrated in actually 3 programs, that there was a lot of collaboration between members within each program and between the programs, and to just in general try and improve the quality of cancer research, recruit the next generation of cancer research faculty. And I did it for nearly 10 years, and it was a lot of work, but I think I knew how important it was to the Institute. Since I stepped down in 2016, there have been a number of changes at NCI. They've actually put additional requirements in place, like local education in the community, and for a while, up until this year, diversity initiatives. So there's a lot more administrative work that is involved now in maintaining your Cancer Center Support Grant. Going forward, it's hard to predict. And I think Reuben Shaw, who took over from me, has done a great job, but he's finding it very challenging to make sure that we bring in enough cancer research funding to justify our support grant. We have to have some minimum number of federal funding to justify us being maintained as a cancer center. So
high quality,
right? And Salk has, over the last 50 years of the cancer center, we've made a number of major discoveries that have led to progress and better treatments in cancer.
Top premier institutions.
Right. No, I think we would rank as one of the best. Yes.
Yes. So since your cancer center is only for discovery and not having any clinical research programs, and it's probably very difficult to attract pharmaceutical industry funding, right?
Yeah, we've had limited pharmaceutical funding a few collaborative agreements, nothing major right now. Other institutions have a different philosophy about this, and
Right.
have done deals with companies.
And they have clinical trial programs. The pharmaceutical
Right.
companies
So
would sponsor that. So
Right.
that is a good source of indirect cost.
It would be indeed. So what our philosophy to translating Salk discoveries was to set up biotech companies, or at least for individual investigators, set
Yeah.
up biotech companies, and several companies were founded through Salk intellectual property.
Any of your discoveries formed companies out of Salk?
No, I was a co-founder of a company called Signal that was developing kinase inhibitors, but nothing specific that was based on my discovery, other than the kinases are good targets for cancer drugs.
Mm-hmm. And how successful is this company?
It has been reasonably successful. It was acquired by Celgene.
Oh, that's very successful.
And
That's
then
considered a
Celgene
good
in turn
example
was
of
acquired.
return.
Celgene in turn was acquired by Bristol Myers Squibb. So yes, it was being quite successful.
So the journey for being a discovery research scientist in the lab and being a co-founder for this biotech company and witness it to be acquired. What's your reflection on this?
Well, I'm pleased that it was successful. As you know, many biotech companies don't make it.
Yeah.
Right.
So you have 3 good lucky shots, and
Right.
you must work very hard.
Well,
to
it's not
prepare yourself for multiple shots in success.
Right. Well, research is not a 9-to-5 job, so you have to invest a lot of time in everything you do, not only your research, running your lab, your administrative responsibilities, as well as, any outside. You're allowed, in principle, by NIH to spend 20% of your time and in anything other than, outside your research.
So you mentioned you do a lot of whitewater rafting. And how do you find time to do that? And I bet while you were rafting, you can't think of any lab experiments.
That's one of the beauties of being out in the wilderness, is that you can relax, forget all concerns of your day-to-day life as a scientist, and just enjoy wilderness. Some of the river trips, like the ones through the Grand Canyon on the Colorado River, take 3 weeks. And so you're down at the bottom of the canyon for 3 weeks, not worrying about anything. And so it's a great way to relax and to recharge after, all of your efforts in the lab.
It's very hard for me to be completely unplugged for even 1 week.
Right.
And so I need to learn from your experience, right? It's hard.
Well, when we started doing this in the 1970s, there were no cell phones, no sat phones. So there was literally no way for you to communicate with the outside world. So
you're used to it.
Yes. Now, of course, you can have your sat phone and call in from anywhere, even at the bottom of the Grand Canyon. But
maybe that was where you were when we called you from the committee call when you were selected as the winner of this year's St. Gyorgi Prize. The committee was all waiting there trying to say the congratulatory remarks.
I wasn't on a river, though. I haven't been on a river for a few years now. It's physically quite challenging.
So
to raft and because we used to run all our own trips. We didn't do commercial trips. So.
Oh wow, that's
we
amazing.
owned all our own
Lots of
equipment.
planning. Yep. What's your view of the future for cancer research?
That's a very exciting time, and we're just learning huge amounts still. New principles are being discovered. Our own emphasis, we're working on pancreatic cancer now.
Oh, that's the last frontier, right?
It's one of the worst cancers, and it's always detected so late that it's really difficult to treat. I think we're interested, like many people now, in cancer as a tissue. You've got to understand all of the interactions between not only between the tumor cells themselves, but all of the other support cells.
Microenvironment.
The microenvironment, the tumor microenvironment. And we're working on, have been for a few years, on crosstalk between the tumor cells and the cancer-associated fibroblasts, which make factors that support the tumor cells. And we see that as a potential target for the new types of cancer therapy.
That's exciting.
It is exciting, yes.
I'm so glad we have this chance to sit down and talk about your scientific journey and even your White River rafting experience. It's amazing. You can do all of those challenging endeavors in life. So thank you very much for having this conversation with me.
Thank you very much. I've enjoyed it a great deal.
Thank you for listening to this episode of All Things Cancer. Be sure to subscribe so you never miss future conversations. To learn more about how the National Foundation for Cancer Research is working with the global research community to make cures possible, visit nfcr.org. You can also reach us directly at 800-321-CURE.